Okay, the quiz, remember, next week on Monday. In preparing for the quiz, I have posted, I thought there weren't quite enough practice problems for quiz 4, so there are two new practice problems, one called 2G and 2H. These are practice problems from another class I taught, which is very similar as well. So there are lots of problems related to conservation of energy here. Okay, so you can take a look at those as well, 2G and 2H. And I updated the list of relevant quiz problems so that these two sets of problems are there as well. Okay. Any questions about this? All right. Other thing I want to mention is the homework due on Sunday is kind of difficult. Right? I was working through the problems, and I don't write any of those problems, and I came with the impression that they were a bit more difficult than they needed to be. So my suggestion is, why don't you start doing the problems and ask me for them during class, okay? And I'll try to help you out as we go along. So have quite a few good examples. Yeah. Okay, the question is, what day do we finish covering the quiz 4 material? Today. We'll finish covering the quiz 4 material today. Okay. Okay, let's see. I think that will turn on. Yeah, okay. Now, let's get this back. Okay, and we'll do the preparation for the quiz like we did last time. We'll have a review on Thursday. We'll do lots of problems between now and then. Okay, so the first new topic we're going to cover is a nice straightforward one where there's not a whole lot of complications. It's called power. Okay, let me close this so you have more view in space. Power. Okay, so in physics, power has a very well-defined meaning. Power is the rate at which work is done. Okay, so it's work per unit time. And the units is 1 capital W for a watt. Maybe I should capitalize the W actually as well. That's equal to 1 joule per second. There is an old unit of power that's also 1 horsepower, HP for horsepower, and that's the old English unit. Okay, and so that's about 746 watts. That's how much horse does, sort of in typical horsey things that they did back then. Pulling, things wrapped to their, doesn't sound very pleasant, but, things wrapped to their shoulders. So if you're exercising on a machine and tells you how many watts you're doing, divided by 746, and that's a fraction of a horse that you're exerting. Okay. So now average power. P average. That will just be, okay, here's a little confusing thing. So this W will be for watts. Now we also use W for work. Okay, so this is, hopefully it's not too confusing. So the W here is for work divided by delta T, for time. I put the little serifs here to make sure you can see the difference between the two. Okay. Typically, we would have a delta in the numerator as well, but the way work is defined, work itself is the change or the transfer of energy. So there's not like a delta going with the work itself. Okay, and then there's also the instantaneous power. And that's just P without the average symbol. And that's just going to be dW dt, the time derivative of the work. Okay. Any questions about that? Okay, now let's consider the special case for a constant force. For a constant force, when we have a constant force, we know that the work done by the constant force is F dotted with D, the displacement. And now, if we want to figure out how much work is done by a constant force, like suppose I'm pushing something with a constant amount of force, and I want to know how much work I'm doing, but then I can calculate how much power I'm exerting. Okay. So then for the power, then power, the symbol is capital P, is the derivative of the time derivative of the work with respect to time. Okay. So I will take the derivative, the time derivative of this guy. That's what work is. So the time derivative of F dotted with D. Okay. Now, if I say that it's a constant force, then this guy is constant. Then the time derivative of this doesn't matter. I can just pull it out. It doesn't change the time derivative. Just the fact of that front. But what is the time derivative of the displacement? What do we call time derivative of the displacement? Yeah, it's a velocity. Okay. So it's the time derivative of the displacement here that will give me something. So I'll end up with F dotted with V. So that's the formula for the power for a constant force. So for a constant force, we have this, that the instantaneous power is equal to the force dotted with the instantaneous velocity. Does everybody follow that? Does that make sense? Okay. Okay, then let's go on. The next topic we're going to cover is about, all right, we're going to do a little bit of calculus here that may not be familiar to everybody, but don't worry, I'll try to explain it. Okay. The next thing we're going to talk about is the relationship between potential energy and the force that a conservative force exerts. So last time we said the following. I talked about lifting my calculator. Okay. I lift my calculator, gravity is doing negative work, right? But it's storing up potential energy, energy is increasing. And so we have this formula that for a conservative force, we have that the change in the potential energy is equal to negative the work done by that conservative force. You remember that? Remember the whole idea if you have a bank, right? If you have this bank with money, you take money out, the force is doing positive work. As a result, the bank account goes down. Okay, so now what we're going to do is consider this conservative force like gravity. And let's consider a small, and what we call infinitesimal. That's the word we use in calculus all the time, infinitesimal. Very small, and you take the limit as the smallness goes to 0. Okay. So consider an infinitesimal displacement, let's say in the x direction. In the x direction. And we'll call that little change delta x. Okay? All right, if it's just an infinitesimal change, just a tiny change, then the force is not going to change much over that little region. So then the work done by this force will be F, let's say the x component of the force, times delta x. Right? Because I have some Fx pointing like this, and then I make some displacement, delta x. The work done then will just be Fx times delta x. Does that make sense to everybody? The y component doesn't matter because I'm only moving in the x direction. All right, but now we said that delta u is equal to minus the work done by the force. So we have also that delta u is equal to minus work done by the force, or minus Fx times delta x. Just taking this here and putting it in for that. Okay, now I'm going to do the sort of thing you do in your calculus class. Sorry about that. We're going to divide both sides by delta x. So then I have delta u over delta x is equal to minus f sub x. All right. The next step you probably have seen before. Now we're going to take the limit. Delta x really becomes infinitesimal. It goes to 0. And then we get the derivative. Du dx is equal to minus fx. Okay. Now, this is actually not the notation that we usually write it in. Usually the notation we use is a different notation. And for some of you, I know if you're taking Calculus 1, you may have not seen this before, but it's just replacing the d's with the curly d's. Okay? And these are what are called partial derivatives. So this is the proper way to write it. It's actually du dx. We still call it du dx, but we write it in this fancy kind of curly way. And this is what's called a partial derivative. It's just recognizing the fact that x is not the only variable. And what you're doing is you're taking the derivative with respect to x, take the derivative with respect to x, and keep y and z constant. Those are the other variables. Okay, that's what it means. We have x, y, and z floating around. We're taking the derivative with respect to x, and we're treating y as just pinned to some value, and z is stuck at some value. Okay. Any questions about this? It's just a derivative, just to keep the others constant. So similarly, you can make the same derivation for y direction and z direction. Then you get similarly du dy is equal to negative fy, and then du dz, if we want it, is negative fz. So what it's saying is that the derivative of the potential in a given direction is negative the force that the force is the negative of the component of that force. Okay, any questions about that? I know that's a little abstract. It's just the formula that connects the force with the potential. Okay, the next thing we do is maybe a little less abstract, a little more concrete. Let's introduce it with this demo here. All right, this is a little sort of air hockey type thing where there's air being blown through, so the friction is not so great. So you can just see what happens when I have one. I don't know what I call this thing. One moving cart. All right, just goes back and these collisions along the walls are what are called elastic collisions. You can see there are little rubber bands here. And what happens is they come with some velocity like this, and it just reverses the velocity. It goes from this direction to that direction. And notice that the kinetic energy is pretty much remaining the same. It's actually doing a pretty good job. I'm amazed it keeps flying at about the same. Usually it's much worse. Now, this is another card that has about the same mass, other than the fact that it has this little thing attached to it. What do you think will happen if I put this in the way of this guy and they collide? Yeah, so let's just see what happens, okay? What kind of collision do we end up getting? See how this guy got all, well, okay, it's not exactly right, but so the point I want to make, I'll try to make it a little bit more dramatic, is notice how this one's at rest, and this one's going to come in, and then this one will grab all the motion of the other one. You see that? And the other way around. Okay? So if you don't believe me, what you can do next time you're on a pool table, take two billiard pool, whatever you call it. Take two numbered balls, not the two balls, but the two numbered balls, and just put one down, take the other one, and hit it with a stick. And you'll notice that as one ball hits the other one, it just, if you hit it head on, the one that you hit will just stop, and the other one will keep going with the same velocity as the original one. Okay. So this is an example of an elastic collision. So that this is an elastic collision, where the initial kinetic energy is the same as the final kinetic energy. It just transfers from one object to the other. Okay. However, if I made the mass of one of the objects different, if I, let's say, take off the mass of this, then it becomes a more complicated collision. It's still what's called an elastic collision, in that the total kinetic energy is the same before and after, but it's going to be more complicated. It'll look more like this, where this keeps moving. Okay. In fact, let me make it even more asymmetrical by putting the mass on this side, and you'll see. Oh, well, now that's just dumb. Okay. I think it's just too heavy. It's too heavy for the air hockey. Okay. Let me make this actually more light. Maybe better. Okay. So now it actually goes backwards. Okay. So these are examples of elastic collisions. We had already discussed examples of inelastic collisions where they stick together. Oh, okay, the bell curve is not. Okay, now let's go. Okay, that's an inelastic, perfectly inelastic collision where they stick together. In this case, the kinetic energy is not conserved. You lose some energy in actually making them stick together. Any questions about this? All right, so let's discuss what's going on here. So we're going to talk about elastic and inelastic collisions. Oh, yeah, I forgot the fun demo too. Yeah. This is the surprising one, right? This is to show elastic collisions. What's going to happen is, well, I'll just do it and you just watch it happen, okay? Okay. Anybody can explain why that happens? Okay, let's make it a little simpler. Well, okay, the bottom one's done from that, so I can't do that. I was going to do it with only two. So you can do it with a basketball and a tennis ball. Why is it so sticky? Sorry. But I can explain what's going on. Maybe I should fix this so that is you have, let's just consider with two balls, okay? We have a big ball and we have a little ball, right? What happens with the big ball, when it hits the floor, it was going with a velocity v down, and then it reverses and comes up with a velocity v, okay? Now, the small ball is coming down with a velocity v, the big ball is coming up with a velocity v, and as a result, when it bounces, it actually comes up with more than its original velocity. Okay? Now, if you have a third ball, it sees this second ball coming up quite fast, and it will collide and come up with even more faster velocity. Okay? And then that's why with the fourth ball, it just zips off several times, many times faster. Okay? It's all about elastic collisions, which I'll explain here. Okay, so elastic. So think of a hard rubber ball. Okay. Inelastic. You just think of two cars smashing each other. So there's kinetic energy loss in that collision. Okay, the first thing I should mention for any collision, I know we already did collisions, but we didn't have this concept of kinetic energy and stuff, so we're kind of going back to it again. For any collision which is isolated, for any isolated system, the total momentum is conserved. Okay, so remember what momentum is. Momentum is P is equal to M times V, where V is the velocity, M is the mass. So when I talk about the initial, so if I have the initial total momentum, it must equal to the final total momentum. And the pieces we have are, we have, let's say, mass 1. So we have two things colliding with each other. M1 times V1 initial. That's the initial velocity for 1. And then we have M2 times the initial velocity for 2. And then that's equal to M1 V1 final velocity plus M2 V2 final velocity. Okay? So we did this already. This is just momentum conservation. This is quiz 3 stuff. Okay. Now the added ingredient is that for inelastic collisions, this is all we have. For inelastic collisions, that's all we know. And in fact, for a general inelastic collision, you very often don't have enough information to actually solve for what happens, because it can be very complicated. You don't know how much damage is done to your car. You have to know how much damage is done to your car to be able to determine the exit velocities of the two vehicles that are okay. But in the case for elastic collisions, for the elastic collisions, the kinetic energy before, sorry, I should say kinetic energy before and after are the same. Okay, in other words, we have the initial kinetic energy of everything is equal to the final kinetic energy. So what is the kinetic energy? It's 1/2 m1 v1 initial squared, the speed squared, plus 1/2 m2 v2 initial squared, And then we have it for the final case, 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared. Okay? Any questions about this? So in my notes, or usually to make this short, I usually say kinetic energy is conserved. But that's not exactly correct because when two objects collide, when they're touching each other, there's some conversion of the kinetic energy into potential energy of, let's say the two springy objects that were colliding. Okay? So in the split seconds in which they're touching each other, the kinetic energy is not conserved. It's converted back and forth. But it's only the total mechanical energy that's conserved. But when they're far apart again, the important statement is that the initial kinetic energy equals the final kinetic energy. And so for my book, we can just say it's conserved in that sense. Okay. Any questions about that? Okay. Now, I should mention solving these problems can be really quite challenging, especially if you've played billiard ball, pool, you hit balls against each other, you can have them not be a head-on collision, and you can have it go on various angles, right? So then you'd have to solve for conservation of momentum in the x direction and the y direction, and then you'd say, okay, then the kinetic energy is the same before and after, and it's a pretty tough problem. We're not going to go into the full depth of that problem because that would be kind of unfair, I guess. It would be a little too challenging. So let me just tell you one particular case where there's a little bit of simplification that occurs. So let me tell you the case if everything's head-on. So if the collision is head-on, and every velocity is along the x-axis, then we can simplify it a bit. Then we can write kinetic energy. What else say conservation, even though I told you it's not exactly the right statement, just the initial is equal to the final. We have m1, 1/2 m1 v1 I x. So I'll put the x up there just so that you know I'm talking about the x component. Okay? So, but I have to square it, so it looks kind of ugly. And then I have 1/2 m2 v2 I x squared is equal to, is everybody following me? I know there's all these indices everywhere. This is just particle 1, the initial x component. Nothing scary about that, right? Okay. And then particle 2, initial x component. And then I have m1 v1 final x squared. I'm running out of space here. m2 v2 final x squared. Okay. And then for momentum conservation, for that case, we have m1 v1 initial x. That's the momentum in the x direction, plus m2 v2 x is equal to m1 v1 final x plus m2 v2 final x. Okay. Again, is everybody all right with this? Just momentum conservation in the x direction. Okay. As you might imagine, this is not so fun to solve. You can imagine right? You can imagine having maybe two unknowns with quadratic equations flying around. You've probably not solved equations with two unknowns with quadratic equations before. It can be done, but it's kind of awful. Okay. All right. So let me tell you a trick. So with a little bit of algebra, we can actually take this equation and make a little trick to make it go away. Go away in the sense I'll give you something simpler. Okay. So with a little bit of algebra, we can replace the quadratic stuff, quadratic equations, with something very simple, that v1i initial x minus v2i initial x is equal to the negative, and I'll give you an interpretation for this in just a moment, v1 final x minus v2 final x. Okay, so this here is the initial relative velocity. This one here is the final relative velocity. What I'm saying is that the relative velocity between in a elastic collision, the relative velocity between the two colliding objects just reverses its sign. Right? Let me try to convince you that this makes some sense. Okay? Let's consider the very special case where, let's start this again, where this object is colliding with this, which is attached to the table, where the table is attached to the rest of the Earth. Okay? So this is the collision between this object here and essentially the rest of the Earth. Well, okay, it's attached to it. Okay? So this is essentially infinitely mass, having infinite mass. But watch what the relative velocity does. It just reverses its sign. Okay? It doesn't change its magnitude, it just reverses its sign. It was going that way with, let's say, 10 meters per second. Now it's going this way 10 meters per second after the collision. The same thing happens for any elastic collision, that the relative velocity just flips its sign. It just reverses. Okay? Does that make sense, everybody? Okay. That's what this equation is telling you. There's a shortcut for doing this. You can skip this equation here and just simply use momentum conservation and this equation, and there are no squares of anything, and it will let you get the answer. Any questions about that? Okay, the derivation. If you want to see the derivation, it's in my notes here. There's a derivation of the whole thing here, but I'm not going to go through it in class. Okay. Let's see. Let me just remind you, though, for the inelastic case, that for inelastic collisions, we only use momentum conservation. Okay? So for example, you remember this completely, we had this completely inelastic collision when they actually stick together. This is a typical example. And the reason this is a popular example to do is because it's actually one we can solve. There's only one unknown. So the completely inelastic collision, we already did this where this objects stick together. Okay. So let me remind you, we have some initial here where you have m1 coming with some velocity v1i, and then here's m2 coming in with some v2i, and then we have some final, okay, where they're stuck together as a unit, and they're moving with some, okay, I made this velocity look bigger than the others, but that was not intentional. V final like that, okay? And so the only equation we can use here, you don't use anything with energy. You can't use energy, because when things stick together, energy is going everywhere, okay? You have bumpers getting stuck together on cars, and we can't keep track of that, But so what we do is we just use momentum conservation. And so the equation we have is m1 v1ix plus m2 v2ix is equal to the sum of these two masses together, moving together, m1 plus m2 times v final x. Right? We've done this before. Everybody's remembered doing this? Okay. So the new thing I want to tell you about this is if you then solve for, let's say they give you the masses, they give you the initial velocities, you can solve for the final velocity just from using this equation, right? And what you'll find is that you'll find that the initial kinetic energy will be bigger than the final kinetic energy. And you can determine how much energy is lost. So the initial kinetic energy is basically 1/2 m1 v1ix squared plus 1/2 m2 v2ix squared, where the final one will just be this guy over here, where we have one mass, both of them together, m1 plus m2 v final x squared. So you'll find that in general, there'll be some loss of kinetic energy. Does that make sense? So the typical question will be how much energy is lost. Now, as I mentioned, there is one very challenging problem in your homework where you will have, it's the ballistic pendulum problem, okay? They do a good job of describing the history. I actually had fun reading it. You have this block of wood. Okay, you don't know what I'm talking about. Take a look at your homework for Sunday, right? And then they talk about a 9mm and 45. Okay, they talk about different bullets, right? And so the problem is you have a bullet coming in to a block of wood, and you want to know how high it goes up, how high it swings up like this, okay? And the challenging thing about this problem is it's actually two very different problems put together. In the beginning, it's a conservation of momentum problem. You have a completely inelastic collision where the bullet hits the block of wood and they move together. It's just this problem, okay? But then after the bullet is lodged into the mass, it then swings. Then becomes a conservation of energy problem. Right? So to figure out how high it goes up, you have to figure out how high up, basically, what is the elevation of the block. Okay? And that will tell you how much potential energy increases. To help you with that, I will. How am I going to do this? Okay, I'll do this in a very easy way. I'll have you click in just for attendance credit for your clickers, and then I'll do the problem so that we don't run out of time, okay? Okay, go ahead and click in, and then we'll do a problem so that I can finish on time. Okay, everybody clicked in? All right, hurry up, click in. There's no right answer. Just press something. All right, I'll just leave it open. You can click it when you can click. All right, here's the problem to try to help you with this part of the ballistic pendulum problem. So this is coming from test 2D, practice test 2D. Okay, everybody's had a chance? No, not yet. All right, go ahead. Okay, so a 30-kilogram child is on a swing. Okay, the child's maximum height occurs when the swing is 15 degrees from vertical as shown. Okay, they exaggerated a bit so you can see the angle. approximating that the child is a point mass, okay, neglecting the size of the child, just take the point. The child is a point mass, and the distance from the top of the ropes to the child is L is equal to 4.5 meters. The question is, what is the speed of the child at the lowest point? So you start the child here, the child swings down. How fast is the child going at the bottom here? Okay. You may neglect air resistance and assume the child is not pumping the swing by doing this with his or her legs. Okay. All right. Stop and think whether you know how to do this problem before we actually do it. I'll just give you a minute to think about do you know how to do this problem. And if the answer is no, then hopefully you learn. So clearly it's a conservation of energy problem. Think about what is the initial kinetic energy? What is the final, what is the initial potential energy? Okay, and then think about final kinetic energy. Okay. We don't have enough time for you to be able to do the calculation, but just think about it. Okay. Any questions before we go over the solution? Okay, here's the solution. Okay, so we're doing conservation energy, but one of the things that's a little bit tricky about this problem is you have to do the geometry. You have to work through the geometry and figure out what is the height difference between the pendulum at 15 degrees versus the pendulum at 0 degrees, okay? That's a crucial thing we need to know. All right, so this is the position initially. This is the position at the final point. We need to know this height difference. So, all right, so what I can do is I can draw this right triangle. I have 15 degrees here. And remember, I told you this ballistic pendulum thing is very much the same way, so that's why I wanted to do this problem to help you. Okay, so we have 15 degrees here. So this side of this triangle will be this hypotenuse 4.5 times the cosine of 15 degrees. And that comes out to 4.347 meters. Okay, everybody agree with that? And then this little piece here, because this is also 4.5 meters, this thing is also 4.5 meters, this little piece will be 4.5 minus this side here, and 0.153. Does everybody see that trick? You got that? Okay, so this whole thing here, from here to there, is 4.5. This hypotenuse is also 4.5. This side will be 4.5 times the cosine of 15. So then this little piece is 4.5 minus this side. And so you get 0.153. Now, we're going to calculate the energies. The initial kinetic energy is 0 because it starts from rest. Let's take y equals to 0 at the final position. So that's mgy initial. Okay, so then the child has a mass of 30. So m is 30, g is 9.8. The height is 0.153. And I get 44.98. Now for the final kinetic energy, I don't know V final, that's what I want, but I can write it as 1/2 mv final squared. So then I have 1/2 times the mass 30 times V final squared is equal to 15 V final squared. And then the final kinetic energy, because that's just at y equals to 0, is equal to 0. Now I say conservation of energy. Okay, Kf plus Uf is equal to Ki plus Ui. So Kf was 15V final squared. This was 0. Then I had 44.98. I can solve for Vf, and I get 1.73 meters per second. Okay. Any questions? If not, I'll see you guys on Wednesday.
Tomorrow.